Hi, I'm Mr. Rast. Today's lesson is going to be about recording and calculating data from hopefully experimentation. When we record data and we do our calculations, we're going to be using two terms quite often to validate or I guess measure how well our work is. The first one is accuracy. Accuracy is the degree of agreement with the true value. And precision is the degree of agreement between several measurements of the same quantity. The thing that really you should be focused on, the most important thing about accuracy, is that accuracy is a measure of the true value. So accuracy is how close are you to what you were supposed to have gotten. Whereas precision, you can be precise but not necessarily accurate, because your precision is how close your measurements are to each other. So precision is how close you are to several measurements of your own measurements, where accuracy is how close are you to the truth, the true value. So I've got some examples here, and I'm just going to pop up the window because these examples are better expressed that way. So if you take a look at these examples, my first example, if you're taking shots at a target and you had this bullet sprayed around like this, and I'll just play it for you. If you sprayed the bullets around like this would be an example of a shooter that is neither accurate nor precise. We didn't hit the bullseye and we didn't group these shots together. In this example, I know you already see where it's going. In this example, the bullets or the shots, whatever you're shooting, are grouped tightly together, but they didn't hit the target. Now, this is something important to note. When you have a situation that is precise, this is very precise shooting, but it's not accurate, this is usually because there's a calibration error. Something like this would be someone that's probably a very good shot, but maybe the scope was off a little bit. So every time they were shooting, they had this kind of error here. So this is usually not because of human error, where this example would more likely be due to human error. If you're not accurate, that's more like human error. When you're precise and you're not accurate, that's usually a calibration error. Maybe your beaker was not calibrated right, or you didn't zero out your beaker, graduated cylinder, or burette, or maybe you didn't zero out your balance or something like that. And then the final one, and this is what we're going to be, our goal is in lab, in science, ideal conditions, we want to be both accurate and precise. We want to be on the target, and we want to have our data grouped together. I didn't make another video, but I guess we could have done of being accurate but not precise, and I would say that those dots would probably be around the bullseye, never hitting the bullseye, but the average, you could tell, was just right around there. All right, so I hope you understand the difference between accuracy and precision, and that's two things that we're trying to accomplish in lab. Now, when we're measuring things in lab, it's constantly going to show a degree of precision. If I was going to measure out 25 milliliters in a burette and 25 milliliters in a beaker, the scaling might look something like this, where on the burette we have a millimeter and then 10 increments and another millimeter, where on a beaker we might have for every one of these lines, it might be a whole millimeter itself. In other words, one of these lines on a beaker would represent this whole area on a burette, and that's because the burette is very narrow, it's very thin cylinder, where the beaker is much wider. So when we're recording the values off of these instruments, it's very important to report it in a way that tells another scientist what kind of instrument you took the measurement in, because 25 millimeters in a burette is much more precise than 25 milliliters in a beaker. 25 milliliters in a burette using this instrument is much more precise than 25 millimeters in a beaker. So when we do this, if you notice, this is a millimeter and this is a millimeter, so this would be 1/10 of a millimeter. And we could estimate in between these lines, so let's just say this would be 24.0, this would be 24.1. We could estimate in between these lines, and I might say it's 24, like this where the tip of my arrow is, 24.05. It's kind of halfway in between these two. You might have seen the tip a little bit higher as 24.06. That's okay. It's understood that this last number is estimated. If the water went all the way up and stopped right at this point here, I don't record it as simply 25 because this instrument can measure to the hundredths place. So if it was just a little bit above this, wouldn't it be 25? It's not. If it was here, it would be 25.1. So if it was just a little above, it would be maybe 25.01. So just because it lands right on the line, I represent how precise this instrument is by adding these zeros. These zeros tell the reader of your data that I used a piece of equipment that had this much precision in it, more precision. Where in this one here, if it landed right on the 25, if it was just here, this would be 19 millimeters. This would be, I'm sorry, 24 millimeters, and this would be 26 millimeters. So if it was a little bit above, that might be 25.5 millimeters. But there's no way you could measure on a beaker to the hundredths place. You can't estimate there. Remember, this last number is the estimate that's in between the lines. And adding this zero here shows the reader that I used something that measured 25 solid, and this zero was an estimate. I estimated that it was pretty close or right on the line. And again, this one here, I measured to the hundredths place as far as my estimate. The more numbers you have, the more significant your, the more precise your number is. And when we talk about how many numbers are important, we refer to that as significant figures. So in this example, in these two examples, they have a different amount of significant figures. I'm going to go over the rules. I'm going to go over the rules for significant figures right now. The first rule is any non-zero integer is significant. Non-zero integers are always significant. So I think if you're taking notes, I would highly recommend that you would underline the always. I circled it. I did not underline it, so I will circle it better. Always. Non-zero integers are always count as significant figures. So any number that's not a zero is always a significant figure. So example, in the number 2, how many significant figures would there be? There would just be 1. The number 2 is the significant figure. In the number 27, there would be 2 significant figures, the 2 and the 7. So the number 27 has 2 significant figures. 27.0, don't let this decimal point throw you off. There's 3 significant figures here, the 2, the 7, and the 1. The second rule with significant figures is going to involve the zeros. So I said anything that's not a zero counts. If there's zeros, they have different rules, unfortunately. So there's 3 different classes of zeros. Sometimes the zeros count, sometimes they don't. So the first example here is a leading zero. Leading zeros that precede all non-zero digits. So the leading zeros precede all non-zero digits. So that means there has to be a decimal point. These are the zeros that are holding how small this number is. So if zeros in front of this, they do not count. If you want to underline that, leading zeros do not count. They're just representing how small a number is. And we did a lesson with prefixes. In other words, if I was just to take something and convert a gram into a kilogram, and I have a bunch of leading zeros now, that didn't make the number more precise just because I decided to change the unit. So they just represent how small a number is. So in this example here, all three of these zeros simply indicate the position of the decimal point. the number only has two significant figures. Okay? Leading zeros never count. The next classification of zeros are captive zeros. Captive zeros are zeros that are in between non-zero digits, non-zero integers. So 2,602 or 2,600,002 would have four captive zeros here, because here's a 6, that's a non-zero integer, and here's a 2. These guys here are what we would call captive zeros. And captive zeros always count. Remember, leading zeros never count. Captive zeros always count as significant figures. So if they always count, this number would have 7 significant figures. 1, 2, 3, 4, 5, 6, 7. These zeros are not leading zeros. They're in between non-zero integers. So don't get confused on the two. These are captive zeros, and since captive zeros always count, this would have 4 significant figures: the 1, 0, 0, and the 8. Working near an airport. Sorry about that. Zeros, the third classification of zeros are trailing zeros. These are zeros to the right of the number. Now, leading zeros never count. Captive zeros always count. Trailing zeros sometimes count. Isn't that frustrating? They sometimes count. They are significant only if the number contains a decimal point. So these guys only count if there is a decimal point. So they sometimes count. So let's give some examples of trailing zeros. This is the number 100 written 3 different ways. I just wrote 100, and then I've got 100 or 1.0 times 10 to the second, which would be times 10 to the second would move the decimal place over twice. And this is 100 with a decimal place. This is the same number, but showing a different degree of precision, a different amount of significant figures. Just simply writing 100 has one significant figure. It's kind of a round off. I think of this number as a lot of times when people are going to purchase something, you might say, "Oh, how much was that?" It was about $100. We all know that it wasn't most likely $100.00. It was probably somewhere close to $100. It might be $98.37. That wouldn't surprise us because the person told it to us with one significant figure. Whereas because these guys don't count, there was just one significant figure. These trailing zeros only count if there's a decimal place. In this example here, the 1 and the 0 count. Because there's a decimal place, this 0 counts. So this number would have 2 significant figures. And this example of 100, because there's a decimal place, would have 3 significant figures. Pause the video for a second and see if you can write 100 with 4 significant figures. Pretty easy question. Let's see if 100 with 4 significant figures would be 1, 0, 0, 0. 1, 2, 3, 4. And you could write 100 with as many significant figures as you want. Just add more zeros. The last thing I want to talk to you guys about with significant figures is exact numbers. With exact numbers, they do not limit your significant figures when you're doing calculations. If you're using an exact number in a calculation, it does not limit how precise things are. There is no precision in exact numbers. For instance, 1 inch equals 2.54 centimeters. This is an exact number. 1 inch is exactly 2.54 centimeters. So in this here, 2.54 centimeters is not 3 significant figures, and the 1 inch is not 1. This is an equivalence. This is something that is an exact number, and therefore this does not have significant figures. This would not limit you in a calculation. Also, an example of things that would not limit you in significant figures is things like counting. Counting is not a measurement. There are 3 apples in this picture. There's no way to be more precise about that. Significant figures deal with precision, and there's no way to be more precise than to say that there's 3 apples. So counting does not limit your significance in your significant figures. All right, so what I'd like you guys to do now for your first topic, third classwork, is to calculate these guys, and that's very easy. You can even use a calculator. I'm not asking you to do this longhand. So this is a very easy math task, but this is a science class. So what you have to do here is multiply things together and answer them with proper significant figures. And don't forget to answer them with proper units. I'm going to give you a couple examples of how this would be done. So in my first example, 75 inches times 38 inches. 75 inches times 38 inches. You're allowed to use a calculator, so we go 75 times 38 equals. So my answer is 2,850, and an inch times an inch is an inch squared. Now, this has 2 significant figures, and this has 2 significant figures. Therefore, my answer, when you're multiplying values, you can only, or multiplying or dividing values, your answer can only be represented with as much significance as your measurements. In other words, a calculation doesn't make your experiment more precise. This, remember, zeros don't count. So this number right here has 1, 2, 3 significant figures. This number is more precise than my measurements. You can't do that. You can't have more precision just because you multiplied things together. So we would have to record this with 2 significant figures. So that means I would stop at the 8. If it's a 5 or greater, it's going to round the 8 up. So to answer this question properly, it would be 2,900 inches squared. That would be how you would answer this. Okay? So this is the task here. Yeah, I know we can take a calculator and do this part. The task is to write the answers with proper significant figures and also with proper units. That's what your goal is here. Let's look at the next one. It is 10 grams divided by 3 millimeters. So we can say, or it's 10.0. Is there supposed to be more to my calculator? There you go. There's my 0 is missing. So 10, we can put the 0.0 just because it's there. Divided by 3.0. These zeros wouldn't change the answer, but let's just put that there because this does indicate how many significant figures you have. So I've got this number. Oh my gosh, there's 3s and 3s and 3s, and this goes on for infinity. It just never ends. And a lot of times people will write this and just write a bunch of 3s. But now look at all the significant figures here. This is a very, very precise measurement. That's ridiculous if you wanted to count out all those 3s. The other thing people will do, it's even worse than writing all these 3s, is even worse than those 3s is writing this 3.3 with a bar on it, that it just goes on forever. That means your precision in your original calculation was infinitely precise. That's a very expensive piece of equipment to make something that precise. So we don't do that. We don't do this. When we get an answer in our calculator, we go back to the question, we go back to our original measurements, and we look at the significance here. In this number here, 10.0, there's 3 significant figures. In 3.0, there's 2 significant figures. So I'm going to answer this with 2 significant figures. So I'm just going to write 3.3, and my units are grams per milliliter. This is how you would do an example of a density problem. Okay? So rounding off properly and showing your units. Sometimes things that are on the top and the bottom of a fraction will cancel each other out. If they're both on the same side, then they would become squared. If there's more than that, it could be cubed. And Yeah, I think, I don't know, they cancel it out. Oh, and if they can't cancel out, then you just keep them. The gram doesn't cancel with the milliliters, so you just keep what it is. Don't panic on it. So let's go back to our classwork. I want you guys to run these in your calculators. Make sure you express it with proper significant figures and proper units. That's the task at hand. Okay? Thank you. If you have any questions or comments, please let me know. I'm here to help.